This conference will now be recorded.
Hello everyone. So last day we have already started the preparation methods of haloalkanes, and some more methods we'll also see today and some related problems. So here the method that we have at first from silver salt of fatty acid. That means fatty acid, which is long chain, a long hydrocarbon chain, and then CO2H group. This type of carboxylic acid is known as fatty acid. And if the acidic hydrogen of fatty acid is replaced by the metal ion Ag+, then it will be called silver salt of fatty acid. And this reaction, it is named reaction. It is also known as Hans-Sticker reaction. Here we have taken silver salt of CH3COO, and that means it is silver salt of very simple acid, that is carboxylic acid, but it is also possible for fatty acid. So when it is reflux, that is this salt, you can also write it in general form, that is R. Suppose if the acid is RCO2H, the corresponding Ag salt will be RCO2, then Ag. And it is reacting with bromine in presence of CCl4, which is the solvent. And what we are getting CH3Br. So if the general form is RCO2Ag, then the product will be RBr. So here R group is CH3, and this CO2 that is removed in the form of CO2. That means it is decarboxylation, removal of carbon dioxide molecule, which is decarboxylation. And this Ag, it is reacting with one of the Br atom and it is forming silver bromide. Fine. So here it is written as single step, but actually it is not single step reaction. Fine. Now here we have a question which is related to Hans-Sticker reaction, and when we will solve this question, then we'll be getting the idea that what are the different steps that are involved in this reaction, because it is not single step reaction. And why we will get that idea while solving this question, because this question is all about the mechanism. It is asking the intermediate in bracket S, that means it may be one intermediate or it may be more than one intermediate. Both possibilities are there. So it is the number of intermediate or intermediates that are formed during the reaction. Now if we look at the reaction, this is Hans-Sticker reaction, C6H5CH2CO2 Ag. So in the previous example, R group is methyl group, but here R group is PHCH2. That means benzyl group. PH, then CH2, and this is benzyl group. This is reacting with bromine and CCl4. See, same thing. We are getting C6H5CH2Br. So here this is the R group. So we are getting RBr. Now here one option or more than one option may be correct. So that is it is written is and R. Now different structures are given. That is PHCH2CO2Br, PHCH2CO2 dot, that is radical. Then Br dot, and the option C is PHCH2 dot, that means benzyl radical. Now if we do not know the details of the mechanism, obviously then we will not have the idea about the intermediate that are formed in different steps. So first we have to see the details of all the steps that involved in this reaction, then only you can answer this question. So this is the mechanism, and here we have taken the general form, which is RCO2Ag. So the first step is in presence of Br2. This Ag and Br, it will form AgBr, and another Br atom that will attach to the oxygen atom. So we are getting RCO2Br. Now this intermediate, you can see this is actually option A, right? Because in option A you have RCO2Br. This is the R group, but in general it is RCO2Br. So option A is correct. Now in the second step, this is first step. In the second step, this RCO2Br, now this O-Br bond is broken, but it is not heterolysis, it is homolysis. Homolysis means one electron is here, this is a radical RCO2 dot, and Br dot, which is bromine radical. Okay. So normally when we break bond, and if it is heterolysis, it is that one atom is carrying positive charge, another atom is carrying negative charge. But if it is homolysis, then both sides there will be a single electron present, and that is radical mechanism. So this reaction is basically following radical mechanism: RCO2 dot and Br dot. Now Br dot is present in option D. So this is nothing but option D. And RCO2 dot, that is present in option B, right? Then this is second step. Now the second step, RCO2 dot, that is now converted to R dot and CO2. That means this bond is broken. So R dot and CO2, that is again decarboxylation is actually occurring in the third step. So R dot that is formed, this is matching with option C, because in our case R group is benzyl group, PaCH2 dot, and that means all these options are basically correct. A, B, C, D all are correct. And finally the termination step, that is further we do not have any other step. Now what is happening? This R dot is reacting with RCO2Br. Now RCO2Br, it is already generated in step 1. So this RCO2Br, as if this CO2 is removed, that is this RCO2 is removed in the form of RCO2 dot. So this Br dot and R dot together, it is making RBr, which is the final product. So in our case R is PHCH2, so that is why final product is PHCH2Br benzyl bromide. So this CO2 dot, RCO2 dot that is formed, it can again start this option 3, because option 3, this molecule is actually, right? So here correct option is A, B, C, D, all these 4. Okay. Another question which is not regarding to this reaction, that is Hans-Dicker reaction, but that is related to preparation of haloalkane. Which reagent will you use for the following reaction? Look at this reaction. The reaction, here we have the starting material CH3, CH2, CH2, CH3. That means it is N-butane, linear chain butane, 4 carbon, and 2 types of products are there, because when one of the CH bond, here CH bond is replaced by Cl, so you are now getting CCl bond. But how many different types of CH bonds are there? These 2 methyl groups are equivalent, same chemical environment. So any of these 6 hydrogen, 3 plus 3, 6 hydrogen, if we remove, you will get the first product. What any of these 6 hydrogen, if we remove, in all cases we will get the same product. And these CH2, CH2, now these 4 hydrogen, their chemical environment is also same. So any of these CH bond when replaced by CCl, now you are getting this second type of product. So this is basically CH bond converted to CCl bond. So we have to use a reagent which can act as chlorine source. Now if we look at option, in all these options you have some chlorine source, but that doesn't mean all these options are correct. Fine. Now why it is so? Because in this reaction, here basically we are converting CH bond to CCl bond. Now this bond, when you are breaking, because to form CCl, this bond must be broken. But this is not very facile process, because carbon and hydrogen, if we consider electronegativity difference, that is not very high. As a result, polarity of this bond is not high. So to break this bond, that process is also energy requiring process. That means the first option, which is chlorine in presence of UV light. Now UV light means it is highly energy requiring process. That is why we are using UV light. This will be the correct option. And why the other options are not correct? Because NaCl and H2SO4, it is actually combined together and it will form in the reaction medium HCl. This H, it will replace this Na, so you will get HCl. But simply presence of HCl, that is not enough that you will you can get this type of conversion. So this is not correct. Then option 3 and 4, in both cases, it is dark condition. Now dark condition means it is absence of light. So here light absent, that is presence of light is necessary because we have to provide energy to break this CH bond. It is energy requiring process, but dark condition cannot be taken. And the difference between 3 and 4 is here you have simply chlorine in dark, and the last one is chlorine in presence of iron in dark. But whatever it is, iron present or not, that is not important. Important thing is in both cases it is mentioned dark, which is not possible. So correct option will be the first option, chlorine in presence of UV light. Okay. Next we have another problem. Which of the following is halogen exchange reaction? So now the question is about you have to recognize the type of reaction, and what is the type mentioned here? Halogen exchange. Halogen exchange means one halogen will be replaced by another halogen. Now to answer this question, common sense is enough. You don't have to know any detailed reaction, that is detailed information about the reactions. That is not required. This is very simple question. Just because from the question itself, it is asking which one is halogen exchange. That means one halogen will be replaced by another one, which you can easily recognize if we look at the equations properly. The first one is Rx in presence of NaI. X is halogen. Now this halogen, in the product side we have Ri. That means X is replaced by I. Now this is obviously halogen exchange reaction. Where from I we are getting? That is iodide iron that we are getting from sodium iodide reagent. So this should be the correct option, right? But why the other options are not correct? In the second option, you have CC double bond. And now after reaction in presence of hydrogen halide, it may be HCl or HBr. It is basically addition of H and X to CC double bond. It is addition reaction. It is not exchange. Simply this CC double bond is present before the reaction, and now you have only one single bond between two carbon, and you are getting one CH bond, one CH. So this cannot be halogen exchange reaction. Then option 3, ROH is converted to RX. That means OH is replaced by halogen in presence of HX and catalyst ZnCl2. So this is also not halogen exchange. It is exchange of HO group by X. And the last one, it is basically toluene CH3 attached to benzene ring in presence of halogen and iron catalyst dark. Here basically ortho product and para product, two types of product you can get. So aromatic H, this H and the para H, any of this H can be removed because methyl group, it is ortho-para orienting, and this reaction is basically example of electrophilic aromatic substitution. And here the electrophile will be generated from X2, which is X plus. Electrophile is, this is actually equivalent to E plus. E plus is the electrophile. So here X2, it may be Br. Suppose if it is bromine, this is the structure of Br2. Now in presence of iron, what it will do, it will try to polarize this Br-Br bond. As a result, one Br will be carrying positive charge, another one negative charge. So from this side, you will be getting the actual electrophile, which is E plus, and aromatic H, that is hydrogen that are directly attached to benzene ring, that will be replaced by halogen. Okay, so ortho product and para product, both mixture of these two you will get, but this is not halogen exchange reaction, so that is why this is also not correct. Correct will be the first one. So is there any doubt? Should I repeat? Next one, in the starting material, a question is given which is containing a reaction. Now this reaction is alkene molecule, so this is alkene because it is having CC double bond in presence of HBr, we are getting A. So what is the structure of A? Different 4 structures are given in option A, B, C, D. Now this alkene is unsymmetrical alkene because both sides of CC double bond are not equal. And this is HBr addition, that is addition of hydrogen halide to CC double bond. Now remember, in last class we have discussed about Markovnikov rule, anti-Markovnikov rule. Now if you are blindly following the Markovnikov rule, what is the rule? The rule says that the negative part of the reagent, that means the negative part in our case is Br minus. So the negative part will be added to that carbon which is containing lesser number of carbon. So if I am marking this carbon as 1, this is 2, obviously carbon number 2 is containing lesser number of hydrogen, so Br should be added to that carbon. But if you are following this, then what should be the product? Then the product should be CH3, CH, CH3, then CHBr, CH2, right? But this is actually not the correct option. And if you are choosing this as the correct option, then the correct option will be option B, because it is matching with the structure of option B. But why this is not correct even after following Markovnikov? Because remember, try to remember, in last class I have also mentioned that simply following the Markovnikov rule, when we are considering the reaction, addition reaction of HX to CC double bond, that simply following the Markovnikov rule is not enough. You also have to take care of the fact whether any rearrangement of the carbocation is possible or not. So if carbocation rearrangement probability is not there, then if you are following the Markovnikov rule, you can reach the correct solution. But if there is possibility for rearrangement, because here the driving force for rearrangement is maybe the carbocation is converted from 1 degree to 2 degree or 2 degree to 3 degree, which is the driving force, because it will always try to move towards more stability. Okay, so in this case also we have to check whether rearrangement is possible or not. So for that, what you will do, first there will be protonation of any of these carbon. So protonation will be obviously in this carbon. Okay, now the reason is, if protonation is occurring at carbon number 2, positive charge is at carbon number 1, and this positive charge is 2 degree carbocation. But if you are doing the protonation at carbon number 1, positive charge will be at carbon number 2, which is terminal carbon, and it is 1 degree carbon. So 2 degree carbon is more stable. So that is why the first protonation, that will be at carbon number 2, and positive charge will be generated at carbon number 1. So see here, if this is 1, this is 2, H plus, that is proton which is coming from HBr, that is actually attached to that carbon number 2. So this is carbon number 2, this is 1, and this is 2 degree carbocation, and there is chance of rearrangement, because if you are shifting this H, suppose I am writing this H in this way. Now hydride shift is possible. Hydride means when H is carrying positive charge, we say it is proton, H plus, but when H is carrying negative charge, we call it hydride. Now H will be, that is hydride, it will be shifting to C plus. As a result, now the positive charge is at this carbon, and this carbon is attached to 3 more carbon, that means it is 3 degree. So from 2 degree now you are getting 3 degree, that is the driving force for rearrangement. So this is rearrangement of carbocation. Rearrangement, because the position of hydrogen is rearranged, and after that you are getting more stable carbocation. Finally, Br minus, which is that is H plus, we have already added. Br minus is still in the medium. It will attack this positive charge, and you are getting this structure, which is matching with option A, right? So you just have to check whether rearrangement is possible or not. And here you can say that in the first step we have based on this Markovnikov rule, up to first step you can say that it is following Markovnikov rule, because here carbon number 2 is containing more hydrogen, this carbon is containing less hydrogen, so obviously the positive part of the reagent. Positive part means H plus. Positive part of the reagent that will be added to this carbon. But after that, Markovnikov rule is not followed because rearrangement is there. So whenever you are getting this type of question, just write the mechanism, then you can you will be getting the idea whether rearrangement possible or not, and accordingly you can choose the option. So here option A is the correct option. Any doubt? The major product of the following reaction is, here we are treating para-chlorotoluene. Toluene is CH3 attached to benzene ring, and here we have chlorine substituent at 4 position with respect to methyl group, so it is 4-chlorotoluene. Now we are using two reagent combination. One is chlorine in presence of light, that is HNu, and the second step we are using H2O plus, which is basically H plus in water medium. H2O plus is hydroxonium ion, and this is a sign of heat. Now here we have the reagent chlorine in presence of light, and remember, when chlorine is present, you are using chlorine in presence of light, then aliphatic hydrogen is replaced. But if you are using chlorine in dark or in presence of some iron catalyst, then aromatic hydrogen will be replaced by Cl. But as it is light, that means it is high energy process. Now aliphatic hydrogen means these three hydrogen. It is not aromatic hydrogen, it is aliphatic. So these three hydrogens, there is a chance that it will be replaced by chlorine. So CH bond, that will be now changed to CCl bond. And how many CH bond you have? You have total 3 CH bond. Now if you are considering that it is monochlorination, then the product is CH2Cl, that is one CH is replaced by CCl, and then para position chlorine. But this structure is not present in any of these options. It is closely matching with option 4, but option 4, two hydrogens are basically replaced by chlorine, and that is possible if you are doing using excess chlorine, or you are doing the reaction for long time. Now if this is not the correct structure, so the next possibility is, it is CHCl2 para position chlorine, and it is matching with option 4. But see, we also have another step, which is H3O plus. That also you have to consider. So it is basically, this product will also be formed. That is option 4 product will also be formed, but in the first step. And then after that you are doing hydrolysis in presence of acidic condition. So obviously this is not the end product, right? And you have to find the end product. Now the actual mechanism is, first there is formation of this option 4 compound. See, this is option 4 compound, but you are using H2O plus, though here it is H2O, it is H2O plus. That means it is H plus in presence of water. Now there will be hydrolysis. So these two CCl bond, you can also write it in this way for your, so that you can understand it clearly. So this is the structure, and these two CCl bond now replaced by carbon OH bond. So now you are getting 2 OH. So this chlorine is replaced by OH group. So now you are getting CH attached to 2 OH. Fine. But this is also not the end of the reaction, because when you are getting this type of structure, C attached to OH, C attached to another OH, and there is one hydrogen. Now what happens in this case, as it is unstable, see the mechanism what I am doing, this OH bond will be broken, there will be CO double bond, and this OH is removed. That means it is net removal of H and OH. This H is removed, this OH is removed. So what you are getting? You are getting now C double bond O H. That means aldehyde group attached to benzene ring, and that is mentioned here. So according to that, now our correct option will be option 1. Okay. So this is not the end of reaction because it is not stable. Here OH bond will be broken. There will be CO double bond formation. This OH will be removed. So this is basically net removal of H and OH. You can say it is removal of water. Finally, we are getting option 1 as the correct option. Okay. Next question. The major product of the following reaction. Now this is not aromatic ring because we have only 2 double bonds and no resonance is possible because they are not adjacent to each other. Fine. So as if this molecule is containing 2 CC double bond and you are using HBr as reagent. So this is nothing but addition of H and Br to CC double bond, and finally what you will be getting? You will be getting CH, CBr. This type of addition product you will get. So 2 HBr you are using because there are 2 CC. Now if we follow Markovnikov rule, just focus on this part first. This is not symmetrical alkene. Now this carbon which is attached to methyl, this is less substituted. That means here you do not have any hydrogen, but here you have hydrogen. And according to Markovnikov, negative part will be added to that part which is containing lesser number of hydrogen. That means Br should be added. Br should be added to this carbon, right? Now Br added to the carbon which is containing methyl, that you can find here, first option and also in last option. That means option 3 and 2 not correct. But among 1 and 2, 4, that is if you have to choose between 1 and 4, what is the difference? Here Br is attached to the carbon which is containing NO2 group. Here Br is attached to carbon which is not attached to NO2. But how to decide? Again I am saying, if you are simply blindly following Markovnikov rule, you will reach wrong answer. Because according to Markovnikov rule, this carbon is containing no hydrogen and this carbon is containing 1 hydrogen. So the negative part that should be attached to this carbon, and according to that, correct answer should be this one. But no, this is not the correct option. Now why it is so? See, this Markovnikov rule, it will be successful as long as the group that is attached, it is donating group. For example, the previous CC double bond, you have here methyl, it has plus I effect. So donating group is present, then it is fine. But when there is electron withdrawing group like NO2, as you can see in this case. Now, after the protonation of the H, which is coming from HBr, 2 possibilities are there. Suppose if I'm just drawing this part of the molecule. So if protonation is occurring at the carbon which is already attached to hydrogen, then positive charge will be generated to that carbon which is containing NO2 group. But because of this electron withdrawing effect, this carbocation is not stable at all. So that is why protonation will be at the carbon which is containing NO2 and positive charge will be generated at the other carbon. Finally, Br minus will be added to this. That means correct option will be option 4, not option 1. Okay. So again I am saying here it is true that we do not have any rearrangement, but as the group is electron withdrawing group, so that is why we are not getting Markovnikov rule. Okay. So is there any doubt in these 2 questions? Can I proceed to next slide? So preparation methods of haloalkanes we have finished. And next it is preparation method for haloarene. That means now we will make aromatic organic halide compound. The first preparation method for this is electrophilic substitution. Now in this reaction, here you can see we have taken toluene and in presence of bromine, that is X2, and catalyst you can use two different conditions you can use. One is iron in dark, another one is FeCl3 in anhydrous condition. Now methyl group, it is orthopara orienting, so that is why X, that is X plus, that will be generated from X2, which is actually the electrophile, that will be inserted in the ortho position. This is orthohalotoluene, or it can be inserted para position, so this is parahalotoluene. Now we will see some features about this reaction. First, you have to know why it is called electrophilic substitution. Okay, let me first make this point clear. Why it is substitution? It is substitution because here carbon hydrogen bond is replaced by carbon halogen bond. That is why it is substitution. And why it is electrophilic? It is electrophilic because you are having here E plus, which is electron deficient species. So if it is bromine, it will be Br plus. So this electrophile is involved in the reaction, and the benzene ring, it is electron rich species, so it is actually acting as nucleophile. So the attack of nucleophile, which is electron rich species, that will take place over electrophile, which is Br plus. Now by this method you can easily prepare aryl chloride or bromide. So for that purpose, if you want to make chloride, you have to use chlorine, that is Cl2, and if you want to make bromoarine, then it will be bromine that you have to use. Can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively, according to what you are trying to make, in presence of Lewis acid. And the Lewis acid may be directly, you can take the iron metal in dark, or you can take FeCl3. Now here dark is important because if you are using light, suppose you are using H2, then what will happen? These hydrogens will be replaced, but that we do not want. We just want to substitute aromatic hydrogen with halogens. That is why dark condition must be there, not H2. However, the reaction requires certain specific condition for generation of proper electrophile. So this condition you have to maintain. The ortho and para isomer can be easily separated because you are getting mixture of ortho and para, O plus P. But you can separate them because their melting points are different. So by crystallization, we can do so. Fine. So when there is difference in some physical property, that is melting point or boiling point, then separation is possible. Then reaction with iodine, that is if suppose here we are talking about only aryl chloride and bromine. And what about iodine? Suppose you want to make aryl iodide, that is iodine is attached to benzene ring. In that case, the method is to some extent different. Reaction with iodine are reversible in nature. And that means that when it is true that you will get product, but again it will be converted to the starting material because it is reversible in nature. Now to remove that problem, there is a solution also. So what we can do, we require the presence of an oxidizing agent like nitric acid or HiO4, so that while we are using this oxidizing agent, because the byproduct that will be formed, the byproduct is HI. Fine. So the byproduct that will be formed, this byproduct can be oxidized in presence of this HNO3 and HiO4. And as a result, if the byproduct is removed from the medium, obviously the equilibrium will be shifted from left to right according to Le-Chatelier principle. See, here any of this hydrogen, CH bond is replaced by Ci bond, another I, and H, it will make HI. So this is the byproduct. So if by some process, if you can remove this HI from the medium, according to Le-Chatelier principle, more of this that is aryl iodide will be formed, because now the reversible nature, because of this reversible nature, if you are not removing this HI, the yield of PHI, that is aryl iodide, that will be very low. So that is why here we are using some oxidizing agent which will remove HI from the medium by this reaction. As a result, more of the product, which is aryl iodide, our desired product, that will be formed. Okay. So here slight difference is there compared to aryl chloride and aryl bromide. But you may think that why not aryl fluoride? We have not said anything about this because there are total 4 halogens: fluorine, chlorine, bromine, iodine. 3 we have already covered, but what about fluorine? Remember, by this method, you cannot produce aryl fluoride, and the reason is fluorocompounds are not prepared. Fluorocompound means suppose you want to make pH if, and there may be any other groups at other positions. So to make pH F or ARF, where other substituents are present, better we write as ARF. This molecule cannot be prepared by this method that you can do for other 3 halogen, but not for fluorine, because when it is ARF you are trying to make, obviously you have to use F2. Just in other cases you have used bromine or chlorine or iodine, but the problem with F2 is that it is very reactive. So handling of this reagent is difficult, and even if you get product, suppose you are getting this type of product, but there will be some other undesired product also be there, because F2 is very reactive, and whenever any reagent is very reactive, that means it is less selective. And less selective means even if you are getting the desired product, this one, the yield will be very low, so the reaction will not be fruitful after all. So that is why fluorocompounds are not prepared by this method, but you can make aryl iodide chloride or bromide. Okay, any doubt? So in the previous case we have seen electrophilic substitution. Now other method also we will see, starting from amines by Sandmeyer reaction. So this is a named reaction, and this reaction basically it involves 2 steps. The first step is formation of diazonium salt, and the second step is this diazonium salt now react with cuprous halide, and depending on what type of cuprous halide you have taken, the corresponding aryl halide you will get. So if it is Cu2 Cl2, you will get aryl chloride, or if it is Cu2Br2, you will get aryl bromide. Okay, remember it is cuprous. Cuprous means when copper is having oxidation state +1, and cupric means when it is +2. Now in this reaction, starting material, obviously it is amine, but aromatic amine, and remember it must be primary amine. And primary amine aromatic means there will be benzene ring and NH2 group will be attached. Why it is primary? Because nitrogen is attached to one substituent and 2 hydrogen. So it is primary amine, but it is aromatic amine. Now the first step, that is how we will make diazonium salt. What you have to do, this primary aromatic amine, the simplest structure possible is aniline, PHNH2, where you do not have any other substituent. So suppose we have taken aniline and you are treating it with sodium nitrite in presence of cold mineral acid. Here the condition cold is very important. Why? Because diazonium salt is not very stable. So if somehow you are not able to maintain low temperature, then diazonium salt, as it is very unstable, it will be, even if it is formed, it will be decomposed or it will be broken. Okay, so that is why cold condition must be maintained. And mineral acid means mostly we take HCl and diazonium salt is formed. So this is the first step. Here we have taken aniline in presence of NaNO2 HCl. Temperature is low, 0 to 4 degree. You have to maintain this condition, and these two reagents together, it is actually making HNO2. So this Na is replaced by H. So now you are getting nitrous acid, HNO2. HNO3 is nitric acid, HNO2 is nitrous acid. And you may think that why we are not using HNO2 directly, because this molecule is so unstable you cannot use it directly. We use mixture of NaNO2 HCl so that in the reaction medium HNO2 is formed. So here H will come and Na and Cl together, it will make NaCl, the byproduct. And from NH2 now you are getting diazonium salt. So here it is written, see, pH then N2 plus Cl minus. But if you want to know the details of this structure, it is actually like this. N, then triple bond N. Now this nitrogen is positively charged because it has total 4 bonds, and the counter ion is Cl minus that is to balance this positive charge. So that is it is written in this way, pH N2 plus Cl minus. But this is not end of the reaction, this is just the first step. Now in the second step, mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide, that is, it may be Cu2Cl2 or it may be Cu2Br2, results in the replacement of diazonium group by Cl or Br. Okay, so in this way we can get aryl bromide or chloride. But you can see you can also make iodobenzene or fluorobenzene. So this is the diazonium chloride. When you are using CuCl, there one thing I want to mention, that sometimes cuprous chloride it is written as Cu2H2. Sometimes it can also be written as CuCl. Both are fine. So in presence of CuCl or Cu2Cl2, you are getting chlorobenzene, and this part is removed in the form of nitrogen. There is a sign like this, which means it is gaseous in nature, it will escape from the medium. Then if it is CuBr, HBr, you are getting bromobenzene. If you are using Ki, that is if you want to make aryl iodide or we can say iodobenzene, now the condition is slightly different. You have to use Ki, you have to warm it, then you are getting PHI, again N2 is removed. And if you want to make fluorobenzene, now see, by Sandberg reaction you can make fluorobenzene, which you have seen is not possible in the previous case, but now it is possible. In presence of NaNO2 and HbF4, which is basically the source of fluorine, temperature 270 to 278 Kelvin C. This is also very low temperature, that is around 0 degree centigrade, right? 0 is 273 Kelvin, so this is around 0 degree. And because this fluorinating agent HbF4, this is not very stable, and also diazonium chloride it is not stable. So that is why we are having this type of cold condition. But for Ki it is, you can warm it because Ki is not so unstable. But in this case, this molecule is reactive, so you have to maintain low temperature, and you are getting fluorobenzene. Replacement of diazonium group by iodine does not require presence of cuprous halide. That means you don't need Qi. It is done simply by shaking the diazonium chloride, diazonium salt, with potassium iodide. And why it is called salt? Because it is carrying some positive charge and negative charge. There is ionic nature, so that is it is called salt. So these methods, all these 4 reactions, is there any doubt? Should I repeat? Next method. Again we have taken diazonium salt, but here we have slight difference. When it is Gattermann reaction, not Sandmeyer, up to this part it is fine, it is same. But here haloarenes can also be prepared by reaction of benzene diazonium chloride, that is the diazonium salt, with copper powder in presence of corresponding halogen acid. So if your purpose is to make aryl chloride, you have to take copper metal, but mineral acid is HCl, and if you want to make aryl bromide, it is Cu and HBr. Okay, and this reaction is not Sandberg, it is called Gattermann reaction. Then the next method, suppose you want to make aryl chloride, that is chlorobenzene, commercial method, that means you are trying to make in large scale. Then we take the help of Rastrick process. So in this process, chlorobenzene is prepared basically by this method, and we have started from benzene by passing a mixture of benzene vapor. Vapor means benzene normally it is in liquid condition, but when we are saying vapor, that means temperature must be high. See, 523 Kelvin, so this is high temperature, in presence of air and HCl. Now air is nothing but oxygen, so it is actually acting as oxidizing agent. HCl is there, which is acting as a source of chlorine, though CuCl2 is also present. So benzene vapor, Air and HCl, the mixture of these three, it is passed over heated cupric chloride and ultimately you get chlorobenzene. Now regarding this process, we have a problem here. It is asking the raw material for rustic process is, options are chlorobenzene, phenol, benzene and so. Now this is a common sense. Here by rustic process you are trying to make chlorobenzene. So this is basically product. This cannot be the raw material, right? So this is not correct option. Phenol is not correct. Benzene is basically correct because we have started from benzene. This method it involves a starting material benzene. And anisole. Anisole is also not correct. Anisole is having structure OMe group attached to benzene. This is anisole, but this is not correct option. Fine. The problem is saying that the reaction of toluene with chlorine in presence of iron and absence of light, because it depends whether you are using chlorine in absence of light or in presence of light. Toluene is having methyl group attached to benzene. That means there is both aromatic hydrogen as well as aliphatic hydrogen. Now, if you are using chlorine in presence of light, there will be replacement of aliphatic hydrogen by chlorine. But if you are doing this process in absence of light, dark, absence of light means dark, then aromatic hydrogen will be replaced. So this is obviously not correct option, because if you are considering toluene, so option 1 product is true only when you are using chlorine H nu, but that we are not using, we are using dark. So you will get replacement of aromatic hydrogen. So this is ortho hydrogen, this is para hydrogen, and both these hydrogen can be replaced. So this is ortho product, this is para product, but you will get mixture. So that is why the correct option is mixture of 2 and 3. Okay. Next method is related to Sandmeyer's method. Here we have started from aniline. Basically, you have to identify the final product, which is Y. Now, aniline in presence of NaNO2 and HCl, temperature is low, around 0 degrees, 0 to 4. You are getting diazonium salt, and when you are using Cu2Cl2, basically this N2 will be removed in the form of nitrogen gas, and you will get chlorobenzene. So option 1 is correct. And here in the previous slide you have already seen we do not get dichloro substitution. So these two are not correct, right? And this is NH2 converted to N2 plus Cl minus, then it is converted to Cl. So benzene is also not correct. Okay. So correct option is first option. After finishing the preparation methods of haloarene, next chemical properties of haloalkanes. So it is haloalkanes, aliphatic. There is nothing aromatic. After finishing it, we will also see the chemical properties of haloarene. But mostly the chemical properties of haloalkanes are very important. And here we have some category, 4 categories of reactions. Okay. Haloalkanes are one of the most reactive classes of organic compounds. Their reactivity is because of this polar CX bond, that is carbon halogen bond, that we have already discussed in detail. Because when you are having any hydrocarbon, you only have carbon hydrogen bond, which is not very reactive, because here carbon and hydrogen electronegativity difference is not so high that there is some polarity. But when you have any carbon halogen bond, now electronegativity difference is high compared to the CH bond. As a result, there is some polarity, and because of this polarity, they are very reactive compared to hydrocarbon. So their reactivity is because of the presence of polar CX bond in their molecules, and the reaction of haloalkanes, we can have these 4 categories. So the first type is nucleophilic substitution. So substitution reaction means here this X will be substituted by some nucleophile. That is why it is nucleophilic substitution. And this is a broad category of reactions. Mostly this is the main important reaction for this molecule. So that is why we have it at the first point. Then next important reactions are elimination reaction. That means here if we consider any Rx. So in R part also there is hydrogen. Simply suppose if I am writing CH3, CH2X. This is alpha position. With respect to X, this is beta position. So if beta H hydrogen and X is removed, you will be getting some CC double bond. So this is actually the elimination of HX. This type of reaction is also possible. Why we are calling it elimination? Because you are eliminating H and X. And why the first one is substitution? Because from CX you will get C and U, that is carbon nucleophile. And the third category, reaction with metals, and the fourth category, reduction. But mainly remember, these two are very, very important, and questions regarding these two types of reactions are also very, very common. We have the first type. Number one, nucleophilic substitution. So look at the structure that is given in the box. Attacking reagent is some nucleophile. This is a general expression, and you have any Rx. So here we have written it in this way, C and X. Here you can have any other groups present, and there is polarity generated, del plus del. When we use del, when there is we are trying to express partial polarity. When you write C plus and X minus, that means the bond is totally broken between a C and X. But when you are writing C del plus and X del minus, that means partial positive charge is generated, not fully positive charge. So this is in this way we can represent that the CX bond is polar. Now this X will be replaced by nucleophile. So nucleophile will attack carbon, X will be removed. So this is the leaving group. Okay. You can also say that as if X minus is another nucleophile. So if it is nucleophile 2 and this is nucleophile 1, so as if it is replacement of one nucleophile, which is nucleophile 1, you can also call it leaving group because it is leaving ultimately by the attack of the second nucleophile. But we mainly write it in this way, and we call X as leaving group. If it is Br minus, leaving group is suppose if X is Br, suppose you have CBr bond, then the leaving group is Br minus. Okay, so ultimately you are getting carbon nucleophile, and this nucleophile, it may be different types, versatile types may be there. So the reaction in which a nucleophile is replacing already existing nucleophile, which is nothing but the leaving group X in a molecule, that is known as nucleophilic substitution. The CX bond present in haloalkane is polar in nature, and as a result, the nucleophilic reagents are attracted by the partially positive charged carbon atoms. So this is the partially positively charged carbon atoms, nucleophile. Sometimes it may vary. Nucleophile, it can have fully developed negative charge. Suppose if I am saying the nucleophile is Cn minus, so it is having fully developed negative charge, but it may be carrying some lone pair also. Suppose if I am saying that the nucleophile is H2O, so here you do not have any fully developed negative charge, but here the lone pair over oxygen is acting as the nucleophile. Okay, so this can also act as nucleophile. So this negative charge or lone pair, it will be attracted towards the partially positively charged carbon. Fine. So this is the basic principle of this nucleophilic substitution reaction. Okay. Any doubt? Now here we can see variety of nucleophilic substitution, and the starting material we have taken ethyl bromide. So here R group is ethyl. The first reaction KOH, you are using aqueous KOH. So here the nucleophile is basically HO minus. HO minus, it is attacking C2H5, you are getting C2H5, which KBr is a byproduct. Then the next reaction you are using ammonia. Here you do not have any negatively charged species, but lone pair over nitrogen can act as nucleophile. And see here different types of products are possible. So C2H5NH2, this is the simplest structure you can understand. Simply Br is replaced by NH2. But as the C2H5NH2, suppose I am writing it as ETNH2. This is also a potential nucleophile, right? Because it is derivative of ammonia, so it can attack another ETBr like this. So as a result, now what you are getting, Br is removed. It will take one of the H from NH2 and you will be getting ET, then NH, then ET. So this is secondary amine. And if there is further, that is if now it is also acting as nucleophile, now you will be getting R3N. And if R3N is attacking another ETBr, you will be getting this type of quaternary salt of nitrogen. So nitrogen is now attached to 4ET1Br, and when it is attached to 4ET, obviously it will carry some positive charge, and that is balanced by Br minus. So all these types of possibilities are there. Then KCl. Here the nucleophile is Cn minus, negative charge over carbon. You are getting C2H5Cl. But remember, when it is silver cyanide, now the product is different. Now the attack is through nitrogen, not through carbon. Depending on what type of what type of cyanide source you have used, whether it is KCN or AgCN, your product may be different. Why it is so, we will come to that point, not today, in the next class. But remember, depending on the reagent type, you can get different product. Then KNO2 and AgNO2, both are source of NO2, but product is different. It is nitrite, this is NO2, nitrate. Okay, sorry, not nitrate, it is nitroether. It is having carbon nitrogen bond, but here it is carbon oxygen bond. This is also known as Williamson synthesis. Then you are using RONA, basically R prime ONA, which is sodium salt of alcohol. Just imagine alcohol, if you replace H with Na, it will be RONA. So it is basically the source of RO minus, which is the nucleophile, and RO minus is attacking, Br is removed. Then the next nucleophile, NaC triple bond CH. So this Na and C, this is basically like this, Na plus C minus triple bond CH. So this is the potential nucleophile. It is attacking C2H5. You are getting this. Then R prime CO2Ag. Here the actual nucleophile is RCO2. Okay. So today we will not be able to finish it because we need detailed discussion related. So up to this related to any slide, if there is any doubt, please mention. So we are ending the session here as there is no doubt. Thank you for listening.